Hello there guys, welcome back to yet another video on feedback. Now, key thing to remember, everything that we need to be done, we need to make sure that we are doing it fully. So the key idea here is for you to understand. Again, so full understanding. Now, how are we going to get full understanding? Very simple, by having bubble pen, okay, by having full explanation, by having the working out. Okay, now let's get ready. Now we're going to be using the figure here to work out the volume. Now first of all, we're going to use the volume. So what we have is we have volume is equal to mass over density. So all we're doing is taking this and this, we're just swapping the places around. Now the mass we know is already is 3.9 kilograms. Now we're going to be looking for the volume of the wax when it is all liquid. So we are going to go scroll up and then looking for the when it's liquid, so therefore the density when it's liquid is going to be 8 actually, so 8 3 there, and the answer is going to be 0.0047. This is the answer in this case. Now there's nothing to convert, and this is going to give us 2 marks. Now the volume of the wax changes when it is solid. Now first of all, the volume is a liquid. How do we know it's a liquid? It says here because when it is all liquid. So wax, when it's wax melted, is going to be liquid. So this is liquid form. Okay. Now when it's solidified, it's going to become ice, and we can see that the volume, okay, decreases because liquid takes more space compared to solid, so therefore it decreases. Next one. Now, why is it that R to S is shorter, but Q to R is longer? Now let's take a look at where R, here we go. So R to S is shorter. So how do we know? So the time, this time, so this from here to here, so this is the time taken. So T is shorter compared to the time from Q all the way to R. It is definitely all shorter. Now what we are going to say. So first of all, we're going to identify what is going on at Q to S. So pretty much, so Q to R, we have pretty much a change in state. Okay. Now that's the thing that's happening. Change state. Now if it's change state, okay, so change state, and then from Q to S, what's happening? It is cooling down. Okay, so in brackets, we're going to say losing energy. Okay, so it's losing energy in this case. So temperature is going down. Now, if I go here, let's take a look at the results. So which of these two is about Q and S? So latent heat is when changing state. So this is going to be Q to R, and when it is a solid, so this is going to be R to S. So therefore, what we can see that the energy needed to change state is 190, but the energy needed to cool down is 2.9. So therefore, we're going to start with this. So we're going to say is the following. So how would I word this? Okay, let's put this here. So we can say that the specific heat capacity is less than the specific latent heat. Okay, that will give you 1 mark. Now the next mark you're going to say is if you add the numbers. The specific capacity we know is 1.1 kilojoules / degrees Celsius is less than 190 kilojoules degrees Kelvin. Okay, therefore the energy needed to change state is 190. The energy needed to raise the temperature or decrease the temperature is 2.1. Okay, so what's happening here is, okay, so because the energy needed to change state is higher, so because the energy needed, so E needed is higher, it will take more time to change the state, because if you remember, energy is power times time. So we're going to ignore power for now. So since we know change state, specific capacity is greater, therefore time taken is going to be greater. Now here, Q and us. So again, so this is when it is, again, we apply the same situation. So since the energy to drop down in temperature is less, energy is needed to drop down in temperature, therefore the time is going to be less in this particular case. Okay, so we can actually see it from this data here. Okay, so what does it mean? It means that, so if we have less energy needed, okay, so it means that there's less energy, because remember, when things cool down, it needs to lose energy. Therefore, there's less energy transferred to cool it down. Okay, so therefore, if the heat capacity is less, so 2.1 means it needs less energy. So therefore, less energy is transferred to surrounding. Now, here's what's happening. So we have a liquid wax. Okay, it changes state and then it's solidified, and then it cools down even further, so it become a solid in this case. Okay, so this here is QR, and from here to here it's just solid. It just become more solid because losing more energy in this case. Yeah. Okay, for example, you can think of it, if you think of it, you can think of it as water. Water changes into ice. Okay, and then you keep the ice for longer in freezer, so it loses more energy, so therefore it freezes even more. That's to freeze things, you need to make it lose energy. That's what is losing energy. So get one mark for identifying that it is the heat capacity and the latent heat, and then the energy number, and the last one, what's happening with when solid, it's losing more energy. Sorry, it's losing energy, so it's losing less energy because the specific capacity is less. Okay, now remember that the change state is linked to this one, and the cooling one is linked to this one. Now, because we can raise temperature, we can decrease it. Now let's have a go. Now here, there are 3 pins, remember, there are 3 pins. Okay, we've got the earth on top, we've got the live, and then we got the neutral. Okay, now the live is pretty much connected. This here is connected to a fuse, so therefore the answer is going to be the live wire in this case. Now we have a fuse. Now how does the fuse work? Now on the fuse, when the current's too much, so when the current rises more than this, okay, fuse equal to melt. It melts, it heats up, it melts. Okay, so it melts. Okay, and then it breaks. And then what happens to the circuit? Circuit breaks because no current flow. Okay, because current needs to go through the fuse and then to the live wire, and then it goes where it needs to go. Okay, so in this case, so if the fuse is not there, so there's the gap in the circuit. So two marks you get when you say the fuse, what happens to the fuse, and then what happens to the circuit in this case. Now what can we do to add a safety precaution? Again, we can use the earth wire or the earth pin in this case. Okay, so earth wire, earth pin. Now that's one. I'll give you a second one just in case you're not quite sure. So I'll say insulation. Okay, so cables, plugs, they have insulation around them. Now this is a good question that we have. FMA, we're going to rearrange the equation. Again, this is the equation given to you. We just need to rearrange it. So F, M, F we know is a resultant force. So I'll write it down here. Over M, so 0.92 over, here we go. And we are done. Now work out the size of the resistance. So what we have is we have the ball, we've got the weight downwards, we've got the air drags upwards, and we know that there's a resultant force that points down, and this force here is, and so therefore So the resultant force is the weight minus the air resistance. So we're looking for force take away W equal to minus air resistance. So we change the sign, so we have W, so we have W minus F is equal to air. So the weight, do we have the weight? Yeah, 2 point, so the weight is 2.5, take away 0.9, and this is the air, so the air resistance is 1.8, that says 1.58. So therefore, this is 1.58 Newton. And you can actually see that there's a big, and the resultant force that point downwards, okay, is this there. Nice and easy. What 2 marks there. Now power, we're looking for power. Now power is energy over time. Now what we have energy, so what are we doing? So we are going up the stairs, so up the stairs, so this here is GPE, so the energy is transferred to GPE over time. So GPE is mass, gravity and height over time. So mass is 48, G is 10 on Earth, height is 2.9, divided by the time 3.4. Now we need this into SF, so the answer is going to be 1,410. 1,410. Done. Okay, so to SF. Now this one we need to remember the equation again. So how do you remember? So we have current, we have charge, we have time. So current is the rate of flow of charge. So we need to run it for charge. Charge is equal to current multiplied by time, and that is current is 2.5 multiplied by 80. Now 2.5 is millimeters. So sorry, milliamps. So milliamps. So milliamp is times 10 to the power minus 3. So we need to remember this. 1 times to the power of 3. So if you multiply them together, you get 0.2, and the answer for the unit is coulombs, or the units is just C in this case. Okay. Now, if you left it in milliamps, so you can do this. You can do this, for example, or you can do charge is equal to current times time. Current is 2.5 milliamps multiplied by 80 second. Okay, this will give you one maybe without the, yeah. So this will give us, let's say, 200. Okay, and then since we have milli, so we need to put milli coulombs there. So this will also be unacceptable because the answer, because the unit, you put the milli there in the unit, but we need to fix this up. So let's have a look. So 1, 2, 3, yes, correct. So these is all. Okay, so we got, but there you go. Next one. Now again, so we have gravitational field. So we got density, pressure. So pressure is equal to height, gravity, density, gravity. We want to arrange for height, so height is equal to pressure over density times gravity. Pressure 3,500 over. Now look, there's a 3 there, so many people miss out this 3. So therefore, it's going to be 1 power 3 multiplied by 10, and the answer 0.35. Okay, it's 2 marks, and this is the working out there. Yeah, it's 1, 2, 3, 4. So because we need to remember the equation. Now, draw an arrow to show the direction at x. So people miss x. Where's x? X is there. Look at x there. So therefore, the arrow points at x perpendicular. So it needs to be perpendicular to x. Okay. So remember. So write down 90 degrees. Here we go. So we're going to move to the next one. Now we need to be careful there, not to go about the thing. Now, if you see a tick, maybe I've not. I've just put a tick because it's valid, but I may not have counted it because it says here your advice. Plan your answer first. Now, theories, blah blah, Big Bang. So we're talking about the Big Bang. So Big Bang. Okay, so Big Bang. Now, two pieces of evidence. We need two things. So we're going to do. I'm going to split this into two. Therefore, we just need two pieces of evidence to talk about it. The first piece of evidence is going to be the redshift. Okay. The second piece of evidence is going to be the CMBR. Now, redshift. What is the redshift? Start with the redshift first of all. Okay. What is the redshift? Now, redshift is pretty much the absorption lines. Okay. They are shifted to the red end of the visible spectrum. Yeah, that's one. Now, what does it mean when it's been shifted to the red end of the spectrum? Okay, it means that distance, that's the word keyword distance, galaxies are moving away. They're moving away. Moving away where? They're moving away from us. So we need to say it is distant galaxies away from us. Okay, and this is the one that proves that the universe is expanding. So this proves that the universe is expanding. Okay, so this causes an increase in wavelength. So it causes wavelength to increase. Okay, so pretty much redder. Okay, so proof universe is expanding. That's one. Okay. Right. Now, one thing I would like to add in this case is the following. It's redder. Okay. So causing the wave to redder, it becomes redder. Okay. And the moving plus moving away faster. Okay. So faster. So not only that they are moving away from us, but they're moving away faster at a fast pace. So this is the proof that the universe is expanding. The next one we have here, we have cosmic microwave background radiation. Now, what is this? Okay. So this here is what? This is the leftover, the remnant leftover of the Big Bang explosion. Okay. Alright, so it started as gamma rays or gamma radiation. Now I'm going off the lines there, but just for you to understand. Now, because the explosion was so huge, was so pretty much universal, that the energy release can only be released as gamma rays, because gamma rays is the highest energized wave, energetic waves, and it's the leftover of that, leftover from that. Okay. Now, so as the universe cooled and expanded, okay, so it is detected, okay, as microwave, comma, all over the sky. So we detect it now. Since the universe has cooled down and has expanded now, so that gamma rays has been detected as microwave, and it's detected all over the sky. And this proves that the Big Bang theory is correct, and this proves that the universe has a beginning. Now remember, the Big Bang theory tell us that. Now I'll just write it down here. So this is extra. So this is extra. So Big Bang theory tell us that the universe began from a concentrated, okay, tiny point. Okay, all right, just tiny point. Nice one. Next one, this is charged particles. Okay, so one thing we need to remember is it's always, so pretty much it's gaining negative charge. Now, if I draw the atoms there, so atoms, proton, proton, neutrons, I have the electrons around it. Okay, now which of these will move? Okay, so which one of these will move? So again, the positive, the rods, the soot have what? What do they have? What is the soot having in this particular case? So the soot is, okay, it's gaining electrons. So electrons equal to easily removed or added. So it is the electrons that can easily be removed or added from atoms. We need to be careful there. Now, why does it move? So why does the soot move towards the plates? And now what we know is we know that the soot particles are negatively, the soot particles are negatively charged. So these are negative. Now, if they're negative, why do they go to the wall? Why do they go to the wall? It means that the wall need to be positive. So if something is negative, is going somewhere, it means that they need to be positive in this particular case. So this is what we're going to do. Okay, so this is what we're going to do. So we're going to say, okay, so we're going to say, what? We're going to say, alright, so negative soot are attracted. They're attracted to where? They're attracted to the positive metal tube. So what we've done is we know that they're negative, we know that they're attracted to the positive part in this one. So attracted to the positive part in this case, and then finally we're going to say, so opposite. Why are they attracted? Because opposite charges attract. Okay, yeah. Opposite charges attracts. Now, when the switch to metal, the charges pass. Okay, the charge passes change. Okay, when the pulse reaches the metal tube. Okay, here the metal tube. The charge on them changes state. How did it change? Okay. Now, what happened? So now we have positive and negative. So now they have balanced out. So they're balanced out. So positive and negative, they balance each other out. So therefore, what we're going to have is we are going to have the following. So they become neutral. Now, how do they become neutral? For example, if this is -1 and it is attracted to +1, the end product, the result, equal to 0, which is neutral. That's what happened. So these suits here, you can see these suits are -1 and this is +1. So therefore, overall, they become neutral. Now, the tube does not become charged when the soot reaches it. Why is it? So why is it that when the soot reaches them, it doesn't make them like say negative or positive? Why is this? Because, now look at this, because it is a metal. Okay, so why is it that when, so pretty much saying to you, so this is metal. Okay, so why is that when the soot, which is negative, reaches it, why does this one not become negative in this case? So why is this not the case? And this is simple. So metal, they are conductor. Okay, so they will conduct it, so therefore they will move the electrons, the negative electrons, okay, from, okay, they'll move the extra electron from the soot to the ground. Okay, now let's have a understand what's happening. So first of all, the soot become negative because they are gaining electrons. So these guys here, let me just delete everything, they are gaining electrons. Okay, they're gaining electrons. Okay, so these guys here, they gain electrons and minus. Okay, now let me zoom in. Now, when these guys here touches the metal, so this is the metal, so what happens is this electron is transferred to the metal. Now the metal has the electrons. The metal take the electrons because look, it go through it and then it goes down to the ground. Because metal is a conductor of electricity. So that's why if you go outside on a stormy day, you take a piece of metal, you put it in the air, what happens? You get zapped. You get zapped by the lightning because the lightning is like that. So the electrons are transferred to the metal from the lightning to you, to the metal, and then go through you to the ground, and you get zapped in this case. Okay. Now, mean values. This is easy. This is average. Okay, so you know how to do average. I'm not going to do this for you. So much sum divided by the number. Okay, so the sum divided by the number. Okay, so you should be able to, so everyone should be getting this marked there. Yeah. So the answer would be, so add all of them together, and then divide it by 1, 2, 3, 4. Done. Okay, so you should be able to do that. Okay, here's a graph. Force and height. Okay, force and height. Use this graph to work out the height. When it's 80, says 80. So all we have to do is we're going to extrapolate this. Okay, extrapolate this. So 8 is there. 0.8. We go up. Okay, we go up, and then just go across in this particular case. Okay, so somewhere between this reading there. Okay, so somewhere, so it's going to be, for me it's going to be 3.2 newtons. Now work out the gradient of the graph. So we need to work out the gradient of the graph. Now remember the gradient of the graph, how to work out the gradient of the graph. Gradient of the graph is going to be the gradient change y or change in x. So I need to pick two values there. I'm going to pick two values there very quickly. I'm going to pick two values. Any values that's easy to read. So I'm going to pick my first value here, which is this one, which is the one I've taken. And then I'll just take another value, which is easy to read. So I'll take this one there. So therefore I have my triangle from here. So this is my change in y. And this is my change in x. Okay, so pretty much I know that my change in y is going to be 3.2. Take away what is this value there. Okay, let me just read this properly. Which is there. 678, so it will be 0.8 divided by x. It is 0.8 there, which is here. Take away 0.2. Okay, so if you do this with calculator, and I'll get in 4, and this is 4. Okay, now the masking allows a range. So the range that the masking allowed is, the range the masking allowed is, so it's 3.82. Oh, 4. Okay, here we go. Yeah, I'm pretty much in there. So 3.8 to 4. That's the range pretty much. If your answer is in the range, you're going to get your mark. Alright, next one. Okay, so x and y. So y, so this is on the y-axis. This is on the x-axis. So therefore, x is time. Y is velocity. There you go. So what quantities? So these are the quantities. Okay, so these are the quantities done. Now work out m. M is the gradient. So gradient is again change y or change in x. So we need to do that. Again, picking a value that's correct. So I'll pick this one here. So this whole thing. Okay, change y, and this whole thing is going to be my change in x. So 25. 0. Okay, so the answer is going to be 0.1. In this case, let me just double check. 0.1, yep. 0.1, that's the answer. Now what is the C? Now C is the y-intercept. Okay, now this is something that you've done in math, so this is just math stuff. Okay, so y-intercept is where it meets the y, so this is the y-intercept, so this is where it crosses the y-axis, and the y-axis at this point is 0. So the answer is 0. Very nice. Yeah, you get 1 more for writing 0. Now here, we're going to want to be careful, so this is Hooke's law. Okay, now Hooke's law, the energy, so elastic potential energy is half kx squared. So this is the equation. But also, okay, I'm gonna fix this up. So the elastic potential energy is given to us by the area on the graph. Because what we have, the area on the graph, we have the weight, which is the force, and this is extension, which is extension. So force times extension, if you remember, work done is energy, which is force times the distance. So when you multiply them together, it is the same thing as doing the work done. So therefore, work done, the area in the graph is force times distance, and since this is a triangle, therefore it's going to be half fx. So half. So we want to know from 8. So therefore we want to know this one, just this one, just this one. So therefore here the value is d-cat-6, 3.8. So half times 3 times 8. Now 8 is centimeters. We need to convert this to meters. Okay, so we always need to convert this to meters. Therefore the answer is going to be 0.14. Okay. Now next one, find the spring constant. This one, find the spring constant. Now spring constants. So this is Hooke's law. So F is equal to kx. So k is equal to f over x. So from the graph, so k is going to be the gradient. So the gradient. So therefore gradient equal to change y or change in x. So change y over change x. So we're going to do the whole thing. So change y over change x is going to be the whole thing there. So y, the whole thing will be x. So 6 over okay, and the pardon. 5, 3. On va compter 13. Alright, so 6 over 13. Okay. Now remember, this needs to be converted to meters. So times 10 to the power minus 2. Okay, so meters. So this is going to be so I got 46. So I'll say 46. The answer is going to be, again, what do we have on the top is the force, meters, so therefore Newton per meter. Newton per meter. There we go. That's an easy one question there. Okay, blah blah. Now free body diagram is equilibrium, so they are balanced. So if the balance, the weight, so this is the weight, W. Weight is 5. Now it is in equilibrium, so therefore this force here will also be 5. So therefore it's going to be roughly the same length in this case. So therefore it's going to go up by here. Okay, it's the same length. Why? Because it is in equilibrium. Okay. Now, what is the temperature change? Again, we use the temperature change there. So energy is equal to mc delta theta. So rearrange for the equation. Delta theta is equal to energy mass times specific capacity. Energy is 210 times 10 to the power of 3, because there's a kilo there. There's a kilo there. Kilo there. Over the mass, which is this one here, times the specific capacity, which is 8,380. Okay, and the answer we get is going to be about, again, I'm just going to do this to 48.2. There we go, done. 42. Yeah. Now, why is that the temperature increase will be smaller than what you have calculated? So why is that it is there? Now, if you look at the diagrams, where's diagrams? Okay, that's the one. Now, the storage heater contains brick. The storage heater contains bricks. The bricks are heated electronically. Blah, 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 okay, so on. So why is that the energy with the bricks? Now, so this is heating it. Now, let's say we have contain the bricks. We've got storage has a brick heater. There's bricks there. Okay. Now, when we're heating, so the heat will go to the air, will go there, and only some part will go to the brick. The first thing we're going to say is not all energy goes to the brick. Okay, that's the first thing we can say. Not all the energy goes to the brick. Okay. So not all energy goes to the brick. Okay, what else do we have? We have not all energy going to the brick. It means that energy is being transferred to the storage heater part. It's going somewhere else. Now this here will also heat up, isn't it? Okay, so this will also heat up. So therefore, what we have is we have energy transfer to the heater parts, or part of the heater. Okay, so part of the heater itself. So okay, so the thing is here, we want to be careful when we say energy lost. So the masking is ignoring, and so ignore lost, wasted. So if you say these, they're going to be ignored. Okay. All right. Now, what's happening here? The question is, why is it that the temperature increase is smaller than what's calculated? Okay. So one, the value you can. So it means that in theory, this block should be able to heat up by 42 degrees. But in reality, so in life, the temperature will be probably, let's say, I don't know, 38 degrees. So the question is, why is it that in real life it is 38 degrees? What's actually happening? So first of all, not all the heat goes to the brick. That's one of it. Second of all, so if not all the energy goes to brick, where is it going from? It means what does it mean? Okay, it means that the heat has been transferred to other parts. Now we can also say it's been transferred to the heat. We can also say it's transferred to the surrounding. Okay, because this is also valid. It's been transferred to the surroundings. Okay, now look at the words I'm using. I'm saying it transfers to where? To the heater parts, to the surrounding. Okay, and that's why we're getting less reading. Now move to the next one. Now the equation is energy ml. We're looking for energy, so now this needs to be converted. So therefore, 1, 2, 3, so 0.06 times this big number there. So what we're doing is we're changing state. We're making it boil. We are making it boil. So therefore, the answer is 1 point. I think it's 5. If I'm wrong, just check this on the calculator for me. Now, this is work done again. So work done, force times distance, rearranging for distance is work done over force. Work done is the energy, so 4770 over the, and so energy is over the force. Okay, now appropriate number of SF. Now this is where people is going to go wrong. So now what we have is we end up getting 11.35. Now appropriate number of SF. So what you do is look at number in questions. So this here is 1, 2, 3. So 3. So here 1, 2, 3. Here SF 1, 2, 3. So therefore the appropriate SF is going to be 3. So therefore the answer be 1, 2, 3. Okay, that's how we work out appropriate SF. Now here we got so what we have force, we have acceleration. So work out mass. Therefore F equal to MA, and we go to force. A force is 450 over A. Okay, so this is nice and easy there. Okay, and we got this one. There we go, done. Okay, next one. Okay, so next one we have ultrasound. Okay, so the guy emits sound. Sound goes to the wall. It comes back. Okay, so the wall is this many meters from the device. The speed is this one. Work out the time of the pulse and so on and so forth. Okay, all right, let's do this one. So we got distance, speed, time. Okay, now the wave goes. Okay, that this is we know the distance. The speed is this. Calculate the time between the emission. Okay, let's have a look. Detection device emit and detect sound wave. Okay, the emitted pulse will travel to the wall and detect the echo of the pulse a short time later. The wall is 7.5 meters from the device. Okay, now this is this one. So the question says, calculate the time delay. Wait, calculate the time between the emission and the expected. Okay, fair enough. Now let's do this one. So we have distance over this. So distance is 7.6 over 30. Okay, we got this one. So we have 0.03. Now what we need to do is we look for the time between the emission and detection. So it goes and then come back. So therefore it is taking twice as long. So therefore this number needs to be multiplied by 2, and the answer is going to be 0.04. So therefore it's going to take 0.046 to detect it. It goes and then come back twice. Okay, so this is kinetic energy. Alright, so we should know this already. So rearrange. So we have 2 kinetic energy over mass. Square root the whole thing. Okay, so 2 times energy over the mass, which is the whole thing, need to be square root, and then the answer is going to be calculated very quickly. 4 meters per second. Okay, now where is the constant velocity? So I can see that velocity is there. So where is moving constantly? So this is constant. So this is constant. So from here to here. So therefore from 20 to whatever this number is going to be in this case. So therefore from 20 seconds to say 45 seconds there. Okay, done. Next one. Okay, so distance. Distance is distance. Go to area on the graph. So we have the area on the graph. We got. Okay, so we have 1, 2, 3. The area on this. So therefore 1 plus 2, 3. So half time base time height. We're looking for half time base time height. So half time base. So half time base time height plus the square plus the again the half based height. Then the answer is 7. Okay. And to get the full mark, you need to be saying that it is this number here, about. Now, speed, distance, time. So I'm going to use 712 for better accurate answer. And it took 70 seconds, and it's going to be roughly about 10. I think, yeah, 10. I think it to be 10 something. But yeah, let's see. 10.2. Yeah, 10. Done. We have this one. Okay, so this one's easy. So we're looking for potential difference. So we need a voltmeter connected across. Oh, 1 mark. Now we need a variable resistor. Connected with wires. Done. We need a power supply is done. So we need 2 meters. So 1 meter is done. So the other meter is an ammeter. There we go. Done. Okay, so specific capacity of water. I'll come back to this one in a bit. Let's do. Okay, we're almost done. Right. So describe that. So here, as the height goes down, the pressure increases. So that's what we're going to do. So as height decreases, pressure increases. Okay, so pressure increases. Good. Now, why is it the case? How can we now? We're going to be using. How can we use the graph? How did this graph show? Now, this graph show that it is a non-linear graph. It's a non-linear graph. Okay, it's a non-linear graph. Okay, and it is a not proportional graph. So it decreases, but it decreases non-linearly. So there's no constant. It decreases inconsistently. Okay, top of the mountain is this much. Use the graph to estimate this one. Okay, alright, fair enough. Let's go and find this out. 885. They got this width over here. So we go across. And then this will land somewhere in the middle. Somewhere here, I think. Okay. So they got this width. So it's going to be 31.5. Now the range for the answer is the following. The range for the answer is 30 to 34. I am in the range, so I'm good. Okay, now we need to work out the percentage change percentage. So percentage change. So it's just a change. Okay, there's a change. Let's do the change, percentage change. So therefore we need to change means difference. So change means difference. So let's work out the difference. So we know that this is the pressure, and this pressure difference. The pressure is 1. So okay, so pressure at sea level, this one. When the height goes up, so therefore is there. So therefore, when the height goes up, this one. So therefore, this is before. Take it after divided by before. Okay, 100%. This give me minus 28. So change 20.8. I can put the minus. You can ignore the minus. It just changed much. Okay, so no problem. How the power. Now this is a good one. Okay, now the thicker the lens. So this is the lens. So the thicker the lens. Okay, so thicker lens equal to more refraction, means more powerful. And also, if you remember, so we have the line, we got the lens there. Okay, now what we have is we have this point, so F point. Okay, now if the lens is thick, so what happens is we got the light go through, and then the light refract, and it goes through this F point there. Okay, so if the lens is thicker, okay, so it means that the F point is closer. So therefore, when the light goes through the lens, because the lens is thicker, it's going to bend more, therefore it bends more in this case. Now, compare this diagram and this one. Okay, it's a bit similar, isn't it? Okay, did I make them the same? Okay, so look, that's the center. Yeah, make them the same. Let me just fix this up. Okay, so the F point is, oops. Okay, the F point is closer because it's fatter, thicker. That's the word. And go through. Now it's better. You can actually see that here. Okay, it's more. So bend more. Therefore, the next thing we're going to say is we're going to say that the focal point is closer to lens. In brackets, focal length decrease equal to more refraction. Okay, so this is the reason why, and this happened. Yeah, make sure that you add your full ball pen. So this is the full ball pen. And the last answer we're going to be looking at this one here. Investigation for capacitance of water. Okay, good. We're looking for water now. So what we're going to do first of all, we're going to solve the equation. So equation is the following. So equation is energy mc delta theta. And we're looking for the specific capacity. Rearrange it. So energy over m delta theta. Now we're going to add a diagram there to help us out. So what we have is we're going to have a beaker. Okay. Now in the beaker we're going to add a certain amount of water. Okay. Now of course we want to be able to heat the water, therefore we're going to have a heating element in the heat in here. Now this is going to be connected to something. Okay. Now we want to measure the temperature of the water. We're going to add a thermometer in here. So this is the thermometer. Okay, so this is the thermometer in this case. Okay. Now, if you remember when we did the practical, we had a nice insulator as well. So we're going to add an insulator there to make sure that we are not getting burned and the heat is not losing as well in this particular case. Okay. Now, as the water heats up, the steam will leave. So what we're going to add a pretty much a lid on top of it. So we've got the lid there. Lid, insulator. We have water. This is the thermometer. This here is the heating element. Okay. Okay, let's get ready. Now we're going to find a way to work out the. So now let's use this one. So first of all, we're going to find the mass. So mass. Okay, so pretty much. So we're going to take measure the beaker. Add beaker with water on a balance. Okay, let me just make this better. Okay, add the beaker on balance. Okay, and click 0. So click 0. Therefore, when you put in the balance, you click 0, and then add water in beaker on top of balance. Record mass. So this will give me the mass of the water. Okay. Right. Record the initial temperature of water with thermometer. Okay. Set up the apparatus as shown above. Okay, done. Right, so we want to work out the change in temperature now. So therefore, for the change, we need to start the time. We need to start the timer, press the switch. Okay. All right. using stopwatch. Okay. Switch on heating element. Start stopwatch, then switch on the heating element. Okay. After some time interval, okay, stop the stopwatch, record temperature. Okay, so change in temperature is equal to final minus initial. So now we have the final temperature, we got the mass, so mass is done, final temperature is done, so we need to work out the energy this time. Okay, so energy is a measure, energy from device, and the device is called a joule meter. Now a joule meter is a device that's going to give us the thing straight away. Okay, right? Otherwise what we have to do, we need to measure all using energy equal to power times time. And the power is pretty much rating on the on the heating element, and the time is we get that from the stopwatch, and then we can use this one. Okay, so now we know how to work out the mass, we know how to work out the change in temperature, how to work out the energy. All we're left to do is pretty much use the equation to work out what we need to work out. Of course, we can plot the graph, which we can do. Okay, so we can just add that. Okay. Find C, or you can plot the graph as well. So the graph is going to be so Y is going to be energy, X is going to be, wait a minute, it's going to be changing temperature, and the gradient is going to be mass times C, and then you're just looking for C. In this case, you just divide it by M. Okay, so this is one and easy. Alright, so hopefully you are adding full bubble pen, and we need to make sure that we're getting every single point. Anything that you're not sure with, that's why the video is there. You want to know what you don't know. Okay? Alright, peace out.